Hello everyone, Mary here, and we are going to start our big topic of heat. In this big topic of heat, we are going to go through lots and lots of different things. We're going to begin in this video talking about linear thermal expansion and then eventually talk about heat versus temperature. They're not exactly the same thing. Specific heat, a little overview of the laws of thermodynamics, latent heat and change of state from solid, liquid to gas, and conduction, convection, and radiation, those multiple methods of heat transfer. But in this video, it is all about thermal expansion. Now, all matter expands as it gets hotter. And as you know from your chemistry classes and other courses that you've been involved in, matter is made up of molecules, and those molecules are connected by some sort of bonds. Well, one of the things that engineers can imagine or visualize is that the bond is sort of like a little spring. And as this object gets hotter, it's going to have more kinetic energy. And as it has more kinetic energy, it is going to vibrate further and faster from its rest position. So as this vibrates further and faster, this bond gets stretched out, and what happens is it causes the matter itself to expand. Now, a small amount of expansion on a microscopic level can be a visible change in size on a macroscopic level. Here are some examples of thermal expansion. Depending upon where you live in the country, there are expansion joints that have to be put into bridges and overpasses and things like this. And these expansion joists are determined by code, depending upon your climate, if you live in the north or the mid states or in the far south, exactly how far apart you have to have these. But in the summertime, when the asphalt is very, very hot, it will expand, and these will be quite close. And in the winter time, when matter contracts, they're going to be further apart. And if you don't have things like that going on, you get things like this occurring. This was a very hot day, and the roadway actually buckled. Another place that you're going to see this is if you look at power lines. Very often a power line on a cold day is going to be quite taut, and then on a hot day, the lines themselves are metal. They're going to expand a little bit, and they're going to be a little bit droopier. This railroad track was installed not accounting for thermal expansion joints, and when it got hot, the extra space had to go somewhere, and obviously this was a bit of rail line that had to be replaced. This is a fun one, and I don't know how many of you have been to Alaska, but a lot of the Alaskan pipeline is above ground because of permafrost. They want to prevent the hot oil from actually melting some of the ground that would turn to like sludge with the hot oil going through it. So they put it above ground. Well, in Alaska, you know it can get very cold in the winter, but during the endless sunlight of a Alaskan winter, it can get quite hot. So this is an expansion joint in a pipeline. Pretty nifty stuff. One of my other favorite examples of thermal expansion is the SR-71 Blackbird. This aircraft is no longer used for military applications, but it is still one of the prettiest airplanes that we have ever had the fortune of having in our military. It can fly well over Mach 2, 2 times the speed of sound. And many years ago, I was visiting a friend who was at Wright-Patterson Air Force Base down in Dayton, Ohio, and we got on the base, drove by one of these aircraft. I was just so excited to be able to see it close up and in person. And there were all these buckets underneath this beautiful, beautiful airplane just sitting there on the tarmac. And I looked at my friend and I said, why all the buckets? It's kind of like a beauty queen sitting there with dirty toenails. It just didn't match. What's going on? And he explained to me that because of the heat generated due to these high speeds and the high quantity of drag that it goes through, it will actually get so hot that it will land 1 foot longer than it is when it takes off. That is just amazing. And can you imagine trying to engineer something like that that is going to change shape that dramatically? Very often people talk about thermal expansion and they say, oh, okay, you say everything expands when it gets hotter. What about water? Water expands when it freezes. Water is a very odd, weird little compound. Yes, it gets It expands when it gets hotter and it contracts when it gets colder, but it acts really, really weird right around 4 degrees Celsius and its freezing temperature. And it goes down to the bonds of water. Ice, when it freezes, has a very strict crystalline structure, and it actually takes up more space in a solid format than it does in a constantly changing liquid format. So a small little change that has to do with that crystal structure of water, but once it is a solid or once it is a liquid, it does obey these rules of thermal expansion. Now we're going to do some math equations with linear expansion. This is the equation for linear expansion. The change in length of an object is equal to its original length, change in temperature, times alpha. So let's go through what each of these are. Change in length and original length can be in any length units. So you can use meters, centimeters, miles, feet, whatever is convenient, as long as both lengths are using the same units. The change in temperature is Celsius is preferred in the metric system, but you will find charts online that will be in Fahrenheit as well. This alpha, Greek letter alpha, is the symbol that is used for the coefficient of linear expansion. The units are odd. It's 1 per degree Celsius. Here is a chart for linear expansion. And these are numbers, and to each of them you go times 10 to the negative 6th per degree Celsius. So you don't forget to add that times 10 to the negative 6th to these values. So let's actually talk about some places where this linear expansion comes into play. Let's talk about why does running a jar under warm water loosen the lid? Well, if you've got a typical jar, the jar is going to be made out of glass. Glass has a coefficient of linear expansion of 8.5 times 10 to the negative 6th. The lid is probably made out of some sort of metal. Let's say it's made out of aluminum. Well, if it's made out of aluminum, it's 23 times 10 to the negative 6th per degree Celsius. This is maybe 3 times more expansion for the same degree for the aluminum than for the glass. So if you heat up the glass and the jar, the aluminum lid is going to expand 3 times more than the jar will, and it will hence loosen that jar lid. If the lid is not made out of aluminum, but happens to be made out of an iron alloy, it is still a larger coefficient of thermal expansion than for glass. Here's another thing that helps you've seen in your normal life, and that is if you pour hot water into glass. Now, if you've got a typical pickle jar or mason jar or something like that, and you put boiling water into this, the boiling water, what is going to happen? I don't know why I wrote boiling hot, but oh well, Mary does that. The jar actually has some thickness, and what happens is the inside is going to get so hot that the inside of the jar is going to expand. And as that inside of that jar expands, it does not transfer the heat well, because it is an insulator, to the outside of the glass jar. And so this inside is going to expand at a much faster rate than the outside, and that is going to mean that the whole jar is going to be under a stress and it is going to break. Now, if you use something like Pyrex, Pyrex is borosilicate glass. They have added boron and other things to plain old silicon dioxide when they made the glass. And what it does is it lowers dramatically that coefficient of thermal expansion, so that when the glass expands by putting in the hot liquid, it does not expand past the point that the glass can handle that extra little bit of stress and strain. Pretty nifty stuff. All right, next we're going to do a problem with linear expansion, and we'll see you then. Bye-bye.